Yeah, so this is, of course, a specialized audience, so I don't need to introduce this much. We're interested here in doing quantum simulations with these cold atoms, inspired by the wonderful emergent phenomena that happen in materials that are strongly correlated, like Moire or high-TC superconductors. And the big jump in the field came with the introduction of these quantum gas microscopes for studying these Hubbard systems, which allow us now to prepare these two-dimensional gases where you can see every single atom in the system. And it's still amazing to me, even now, that you can think of this pictures before you took the system. It's a quantum system where there's all these correlations between the spins. There's the particles are delocalized, and then you go and take a snapshot. You project onto a particular realization in spin and density, and you can go and measure any endpoint correlation you want of spin and density. All right, so the Hamiltonian that they naturally realize, we've already discussed the Fermi-Hubbard model. So I'm just going to flash through the slide very quickly. Where, of course, it's been studied for a long time with these square lattices because of the connection to high-TC superconductivity. And the big advance in the last few years has been kind of moving away from these square lattices to novel lattice geometries. OK, so a bit of history here. So shortly after these microscopes were introduced, people started looking at the half-filled phases. So here are some pictures from Marcus's group where you can see here the Mott insulators with 1 atom per site. And then here you can measure the 2-point spin correlations and look at these antiferromagnets, which you can now compare to quantum Monte Carlo calculations with one free parameter, which is the temperature of the system. And you can fit the temperature from this, and the state of the art now is about a quarter of the tunneling energy scale. OK, so after people looked at the half-filled systems, they moved on to the doped systems, which are harder for the quantum Monte Carlo to do at low temperatures. And there, the interesting problem is to look at what happens when you dope the antiferromagnet. How does, for example, a whole dopant move around in the system? So in my group, we approached this in a sort of more bulk transport approach, where we were trying to measure the resistivity, not directly, but through the Nernst-Einstein relationship, linking this resistivity to the microscopic diffusivity, which we could measure by looking at the decay of charge density waves in the system. So we would set up a charge density wave in the doped Hubbard system that's strongly interacting, and watch this charge density wave decay and extract the diffusivity, and from there obtain the resistivity. And we studied its temperature dependence, showing that there's this interesting regime at intermediate temperatures where there's a linear resistivity, analogous to what you have in the cuprates, but it's a different type of strange metal. Here, the temperatures are much higher than what you have in the cuprates, but they're not also in the high temperature limit where things are very well understood. So the microscopic version of this was done in Munich and at Harvard, where they looked at the motion of dopants in these antiferromagnets. If you introduce, for example, a single hole, you could ask, how does that disturb the antiferromagnetic order? And what they were able to see was this hole moves around, leaving behind a spin-on, which it is bound to with a string, this geometric string. And if you think about this in a sort of time average picture, you get these polarons where you've kind of locally disturbed the spin ordering around the antiferromagnet. And those are going to be closely related to what, they're another type of polaron related to the same techniques that I'll show you later for looking at the triangular polaron, triangular lattice polaron. But here, what I want to emphasize is, in this case, there's an adversarial relationship between the hole doping and the antiferromagnetism. So you start from the half-filled system, you dope, and you quickly kill the antiferromagnetism with doping. Whereas you'll see later with the triangular lattice, when you hole dope, it's kind of the opposite behavior, where the hole doping actually enhances the antiferromagnetic order. OK, so in terms of techniques, I was saying there was this shift from square lattices that happened first with experiments from Peter Schaus's group at the University of Virginia, where he built a microscope that's specifically tailored to access triangular Hubbard physics. But then a few groups introduced these programmable lattices where you can start from a square geometry and modify the connectivity of the system. And that allowed, in software, tuning between different lattice geometries. So you could go between, say, in the same setup, just by tuning parameters in software, between a square lattice, a triangular lattice. You've heard about the Lieb lattice, Kagome lattice, honeycomb, all these within the same setup by tuning parameters like the intensity of laser beams or frequencies of acousto-optic modulators. So the setup we're using in my lab was first introduced in the Munich group. So what you have here is this blue laser beam, which is essentially a bow tie lattice. It just goes around and gets reflected from a mirror here. That produces a square geometry that you see here. And then you add on top of that a single laser beam, which is non-interfering. It's a different frequency. So that produces a one-dimensional lattice. And now you can combine these two lattices together by also controlling the phase shift between them by tuning the frequency between the AOMs and controlling the relative depths. And that's what allows you to access these different geometries. So for example, if you park the phase of this lattice relative to this one at the appropriate point, you can get a geometry like this, where you get something that looks like a triangular connectivity. So you can go, for example, between the square lattice and the isotropic triangular lattice. And then for different phases, you can get a honeycomb lattice. And you've heard from Martin how you can use now a spatial modulator to kind of block out sites and access new geometries here, like the Lieb lattice or the Kagome. All right, so I'm going to focus here on the triangular lattice. So the underlying lattice we start with is the square, which has tunneling matrix element T. And then we introduce this extra tunneling T prime. And we can vary the ratio of T to T prime at will. So we can go from the square limit to the isotropic triangle, or if you go to very large T prime, you get these one-dimensional chains. All right, so the triangular lattice is interesting already at half filling. The square lattice, we understand everything in there. You have the Mott insulator, the antiferromagnet, the Neal antiferromagnet. But here, the triangular lattice, it goes back to Phil Anderson. He was looking at the triangular spin 1/2 Heisenberg model. And there, that would be the limit of the Hubbard model at infinite U over T. And so there you have this phenomenon of spin frustration. So if you put antiferromagnetically coupled spins on this plaquette, you see you can decide how to deal with the third spin. And what Phil suggested at the time, that maybe what you want to do is form these singlets and cover the lattice with singlets, and then you have a superposition of all the coverings of the lattice, and that was the beginning of the field of quantum spin liquids. Turns out, it was a great idea to launch the field, but it was actually wrong. So the ground state of the Heisenberg model on the triangular lattice we now know is actually this 120-degree Neal order. That's in the Heisenberg model. But for the Hubbard model, where you now can control U over T, so you're not necessarily in this very large U over T limit, you have a much richer phase diagram. So this is it's only at half filling, okay? And here I'm showing a suggested cartoon phase diagram where you vary T over T prime and U over T. So if you go to the limit where T prime is 0, you have the square lattice where you have the Neal order. If you go to the isotropic point with a triangular lattice, then as you increase U over T, you cross over from a metal at weak U over T to a Mott insulator with the spiral ordering at large U over T. And then in between, people don't really know what's going on. They see some sort of non-magnetic insulator in the simulations, and there's a lot of debate about the nature of the ground state. A lot of people think it might be some sort of spin liquid that breaks time reversal symmetry, a chiral spin liquid. OK, so this is just to show some of the richness of this system at half filling. And of course, it gets even richer once you start to dope. OK, so in our system, we have bilayer imaging, which is also, for example, used in Martin's group and at Munich. So this bilayer imaging allows you to circumvent the issue of light-assisted collisions that you have in the microscopes. So essentially, before you take the picture of the system, you use a magnetic field gradient to separate the spin-ups from the spin-downs using a Stern-Gerlach. And so you can now image both layers simultaneously and get the full spin and density information in the system. So you fully reconstruct on a site whether you have a double-on, a spin-up, a spin-down, or a hole. So you get pictures, the reconstructed pictures like this. And I was mentioning, this was first people looked at the 2-point correlation functions in Peter's group and in Marcus's group. So here's our version of that. Here are the 2-point spin-spin correlation functions in the half-filled system, which is frustrated. And what you expect is at large U over T is this 120-degree Néel order. And of course, this is a quantum antiferromagnet with a lot of spin fluctuations. But here I've overlaid on top of our data, a classical spin pattern that looks like this 120-degree order. And you can see, for example, if you fix, let's say, this spin here, then the nearest neighbor spins are primarily anti-aligned. So they have a negative correlation. And then if you go further out, here the spins are aligned with each other. So they're positively correlated. Okay, and the short correlation length is the fact that, again, we're at finite temperature. The temperatures are usually a fraction of the tunneling. And like about, maybe in our experiments, about 70% of T or so. All right, so okay, so that's at half filling where you have this spin frustration physics. And then the more interesting part, the more that it started with the Moiré systems and then kind of moved to us through Eugene and his student Ivan, was the kinetic frustration that happens due to doping these systems. So Eugene and Ivan were working with Ataç Imamoglu at ETH. And they were doing this experiment that Eugene described where they have these transition metal dichalcogenides, these 2D materials, which you can stack on top of each other and twist them relative to each other to get a Moiré pattern. And to very good approximation, you get a triangular Hubbard model with a very large U. And they have a gate on the system. You can dope between holes and particles. And what they measure in the experiment is the spin susceptibility. So they're able to see that through the spin susceptibility that when they're hole doped, they get an antiferromagnetic spin susceptibility. You go to the particle doping side, you get ferromagnetism. And so Eugene had a microscopic picture of what's going on, and he talked to us and said, maybe you can go and check this out in your experiment. So the key ingredient here is the role of kinetic frustration in the system. And I want to go maybe into a little bit more detail here in explaining how this arises. So I'm going to imagine a system where first you put a single particle in the lattice. And you know what, if you just put a single particle in the lattice, the system wants to be at 0 quasi-momentum. You can get the band structure. It looks like this. And you just want to put the hole here, put the particle here at the minimum, where the energy is lowered by the number of nearest neighbors times the tunneling. Okay, but let's go about this maybe in a slightly more contrived way. So if you think about the Hamiltonian, you just have the tunneling Hamiltonian. And I want to think about arriving at this picture by delocalizing the atom on each bond. And for the appropriate sign of the tunneling, what you want to form naturally is to form symmetric spatial orbitals on each bond. So you form a bond like this, where the phase is the same on the two sides. And then you can do this on the neighboring bond and on the third bond, and this works out. You can cover the entire lattice with the same phase because all these, so you cover it like this, and you get a Q, a quasi-momentum of 0. Okay. So the difference now with the kinetic frustration is instead of considering a single particle in the system, let's consider a single hole in a spin-polarized system. Okay, so we're going to start with spin-polarized and then introduce the single hole. We still have the same Hamiltonian, no interactions here. It's a spin-polarized system. And so it's more natural now to go and rewrite this Hamiltonian instead of these fermionic, particle creation operators and destruction operators. You can write it in terms of hole operators, where H dagger is C. So once you make that substitution, you throw it in there, then the operators are not normal ordered. And so you want to fix that, so you anti-commute them. And that, because they're fermionic operators, introduces a change in the sign of the tunneling. Okay? So now, if you think about the same picture I was describing earlier, if you want to delocalize the hole on this bond here, well, now it wants to form, because you flip the sign of the tunneling, it wants to form a spatially anti-symmetric orbital. Okay? So we do this on the first bond. We do this on the next bond. But then you try to do it on the third bond, and that doesn't work out. So this is very reminiscent of the phenomenon of spin frustration, but now we're talking about the motional degree of freedom of the hole rather than the spin. Okay? So that's what we call kinetic frustration. And in the band structure picture, what this corresponds to is basically you flip the sign of the tunneling, so you're essentially flipping the band structure, and the minimum becomes what used to be the maximum. And because the triangular lattice has this particle-hole asymmetry, now the maximum is at 3T. Okay, so it becomes like you lower the energy by 3T for the hole rather than 60. So it's not as low as the particle is. So how do you fix this problem? So ultimately, this problem, as was described, is coming from destructive interference of different pathways of the hole in the triangular lattice. So they're destructively interfering in this spin-polarized background, and that's what's causing this kinetic frustration. So to remove the interference, what you want to do is to flip some spins around the hole. Okay? And so you naturally want to form this object where you flip spins around the hole and you form a polaron. Okay, so let's understand this a little bit better by thinking about a single plaquette. And I'm going to take the limit of infinite interactions and introduce a single hole in the plaquette. So if you go to infinite interactions, you put a particle on each site. And you can think about this problem, the spin commutes with the Hubbard Hamiltonian. So you can divide into triplet sectors and singlet sector. So in the triplet sector, the only thing that can happen is this hole moves around the plaquette. So let's move it around the plaquette. And nothing interesting happens because it's a triplet. It's a spin triplet. And so, OK, well, now the difference is, of course, in the singlet sector. So now here I've schematically introduced like a singlet bond. And you go around. And now you've picked up a minus sign because you've exchanged the two spins in the singlet. So this minus sign is exactly what you need to cure the minus sign problem that we had before in the spin-polarized system. OK, so this is what you might call a spin-Berry phase. And the spin-Berry phase is what is required to release the frustration energy in the system. OK? So once you do that, you find that for this plaquette, you lower the energy by T for the singlet configuration compared to the triplet. OK, so naturally, you want to have basically anti-aligned spins around a hole. And that's the nature of this polaron that emerges in the system that was predicted by several papers, including from Eugene, in the last couple of years. OK, so this persists outside of this plaquette picture to the more general many-body system. As was mentioned, this problem was actually first studied by Harter and Shastri. They kind of followed in the footsteps of Nagaoka. Nagaoka considered this kind of artificial setup where you take the interaction energy to infinity, and you introduce a single hole, for example, in the square lattice, and you induce ferromagnetism. So Harter and Shastri considered the analogous problem in a frustrated triangular lattice. And what they found was introducing a single hole in the infinity of Hubbard model. So first, if you didn't have any holes, you get, at finite u over t, you get this spiral antiferromagnet. But if you take u to infinity, then the superexchange is vanishing. Right? So you don't expect anything interesting there. But then if you introduce a single hole, what they find in this paper is that you recover the spiral antiferromagnet. But now the antiferromagnetism is not due to superexchange, but it's actually mediated by the presence, the motion of this hole. So this is the kinetic antiferromagnetism appearing in this system. OK, so now let's go to the experiment. So how do we probe this in the experiment? So what we want to look for here is basically the fact that around the hole, you like to form these anti-aligned spins. So you want to look at the disturbance around a hole. And this is using the same technique that was first introduced by Munich in the square lattice. Now we're applying it to the triangular lattice, looking at these connected three-point correlation functions, where so we're asking, we already know that the system has some antiferromagnetism even away from dopants because of this 120-degree Néel order at finite U over T. But we're asking, how does the presence of the hole enhance or reduce the antiferromagnetism? And so here's the 3-point connected correlator, for example, at 10% doping. And you can see, indeed, around the hole, we find in the data this negative spin correlations. And then if you go even closer to the limit of a single dopant, so here we're going to 4% doping, this antiferromagnetic pattern increases even more. OK, so let me comment a little bit about why the spins here why you have these red bonds further out. So I've already explained the antiferromagnetic correlations right next to the hole. So here maybe a simple picture you can have in your mind. So here I've drawn the undoped system with the 120-degree Néel order. And let me introduce a single hole into the system, OK? And let's imagine this hole hopping over here. OK, so we're going to exchange this spin, move it over here, and get a hole over there. So now if you look at, so this is the hole. And then this bond over here, you find that you have aligned spins, which is exactly what you're seeing here. You have the hole, and then you have the aligned spins over here. OK, so this is the whole picture of the whole side of things. You can now go to the particle side of things. So if you now look for particle dopants, doublons, then as you've heard before in Martin-Stokes, then you expect sort of more like the usual Nagaoka story. You don't have to go and do the thing where we had to anti-commute the whole operators. Here you would just work with particle operators. So the system is already, doesn't have the kinetic frustration. And so you naturally form these ferromagnetic correlations around the particle dopant. And this is for a heavily doped system. And then if you kind of go more and more towards the single dopant limit, the ferromagnetic correlations grow further and further out. Yeah. No, this is only in the connected. So I wouldn't, yeah, where the temperatures are a little bit higher. Yeah. All right, so OK, so this is all, the ideal picture here is in the infinite U over T limit, but you could ask what happens at finite U over T. I mean, we are, of course, in the experiment, we are at finite over U over T. So as you reduce U over T, of course, you go from the Mott insulator to the metallic phase. And if you look carefully at the correlations, they have the same signs. So here are the correlations around the hole. Here are the correlation around the doublon. It doesn't really change in terms of sign. Okay, so these are, you're varying the doping and looking at the sign of the correlations. But so just seeing the correlations of the right sign isn't sufficient to claim that you've seen this polaron. Really, you have to combine that with the fact that from measuring the singles fraction that you're in a Mott insulator, so you are in this limit. So basically what I'm saying is already a band structure picture, even in the non-interacting limit, gives you correlations of the right sign. But you combine it with the fact that you're in the large U over T limit measured through a singles fraction, and the fact that you can see in these correlations around zero doping, you see that the strength of this 3-point correlation grows linearly with the doping. So essentially, what you're working with here is if you're going to the limit of a few polarons as you reduce the doping, which are non-interacting with each other, and every time you add extra polarons, just the strength of the correlation just grows linearly. Let me see. So these gray lines are the quantum Monte Carlo, and this would be the non-interacting limit. Okay. Yeah.
And project out the doublons, would the correlations be the same as the non-interacting limit, or does it get modified?
Non-interacting limit. And
so you take basically your non-interacting state, which kind of looks right, and then just project out all the doublons. Presumably, I'd get something that looks pretty similar to the right.
I don't know. We haven't tried that out.
Okay. Fair. Yeah. Mm-hmm.
Comparison to theory, how was temperature adjusted?
The temperature is obtained from the two-point correlation functions. So you, like, for example, you could fit the two-point correlation function, obtain the temperature through that, and then just take that temperature and just here. Yeah. So it's essentially what you can think of our experiment more as comparing the 3-point to the 2-point. So you get the temperature from the 2-point, and you go and fit the 3-point without any free parameters.
And the temperature that comes out is what?
These are about 70% of the tunneling. And the nice thing here, it's a robust phenomenon because it's all kinetic. Yeah. All right, so another thing we can do that's, again, particular to our setup because we have this bilayer imaging is we can go and look at higher point correlation functions. So we don't have to stick with these 3-point correlation functions. We can look at 4-point. And so one of the questions we were asking here is that, we have this finite U over T system. There's already super exchange antiferromagnetism in the system. And then you're enhancing it with this hole doping to introduce the kinetic antiferromagnetism. So now you can go and look at 4-point correlators. And now we're looking here at 2 plaquettes next to each other. And we're just going to look at the disconnected correlator for these 2 spins. So we're going to ask, what does the correlation function here look like conditioned on what's happening on the neighboring sites? So for example, the neighboring sites might have 2 holes, or they might have a hole and a synglon, or they might have 2 synglons, okay? And if you have 2 synglons, well, now, if you're evaluating the spin-spin correlation here, all of these are singly occupied. So there, all you have is super exchange if you ignore, what's happening further away, okay? And then if you introduce a single hole, so here, all that can happen is just super exchange antiferromagnetism. You introduce a single hole, now you open up, or 2 holes, you open up the possibility of kinetic antiferromagnetism. So now we can look at these conditional 4-point correlation functions, and we see that, with the super exchange, the correlations are weak, and then they get strongly enhanced by introducing 1 or 2 holes. Okay? All right, so as an outlook here, so other things we could look at in the future, you've already heard from Eugene this idea of you don't need to just focus on the simplest polaron where you just have a single hole bound to a magnon. You can look at more complicated objects where you can have multiple holes, multiple magnons binding together in this object. And then that opens up the possibility of hole pairing in these more complex polarons. And of course, once you have hole pairing, these holes can condense and lead to superconductivity. And the wonderful thing that was shown by Eugene was, all this stuff is on the scale of T. Of course, the prefactor is smaller than this simplest polaron. So it gets smaller, but it's all T-scale physics rather than J-scale physics. Okay, so that's one of the exciting things that one could look at in the future is, if you could get a bit lower in temperature, you could look at for these more complex polarons. Other things is, so far we've just been taking pictures of these systems. And that doesn't quite prove that you have a quasi-particle. If you want a quasi-particle, you want to do a spectroscopy. So one thing that was suggested, and was actually how people have seen this now in the condensed matter system, is they've looked at things like the binding energy of the polarons in kin phi max group by actually applying a magnetic field to break apart this polaron, the whole polaron. So that has these anti-aligned spins. You apply a larger enough field, and you can break up the polaron and measure its binding energy. That's something you can do in a cold atom system with spin imbalance. Another approach would be to create the polaron with Raman spectroscopy, and that's what I want to now cover in the last few slides. So that's something we've just started exploring. And the idea is inspired by Eugene's proposal. So what we're starting with here is a 2D system which is spin polarized. Okay, so all the spins are up, and maybe you have a few holes in the system. And you already saw from the band structure pictures I showed earlier is that these holes at low temperature want to live at finite momentum because of the frustration. And so what the Raman spectroscopy will do is it will now introduce a magnon to the system. So we're doing a 2-photon transition with the Raman, which is quite challenging because this is lithium and the fine structure splitting is very small. So there's a lot of scattering you have to worry about, but we think now we have everything under control. And so you introduce this magnon, And if you introduce the magnon at the correct momentum, at the correct quasi-momentum by tuning the angle between the laser beams, then the magnon will bind to the holes that are sitting at this finite quasi-momentum and form something like a Cooper pair, something at 0 momentum, but it's now this hole that's binding to this magnon that you introduced into the system. And so you can learn about the energy of this polaron and learn about the binding energy, learn about the dispersion. So these were the calculations that Eugene showed in the previous talk, where you have this magnon this magnon dispersion, and then there's this polaron dispersion that has weaker spectral weight, because here you have to basically flip spins next to holes. So here, there'll be two branches. If you flip the spins away from the holes, you'd get the magnons. But if you flip them close to the holes, you form the polaron. OK, so I want to show you a little bit of data towards that goal. We're still doing this on the square lattice, not on the triangular lattice. In the triangular lattice, if you start from a polarized state, you don't have a polaron. So you just get essentially spin waves. But here, of course, the spin wave story is in the limit of infinite u over t, where you have a Heisenberg model without any doping. But of course, in our system, this is a Hubbard system, finite u over t, finite doping. OK? So we worked hard to achieve very good spectral resolution. So here, this is Fourier-Brodin, but we were able to get a spectral resolution that's about a factor of an eighth of the tunneling. So the tunneling is about 400 hertz. We're able to get 50 hertz. And so here, if you go to a deep lattice, you're just, the atoms are isolated, and you just flip them at the hyperfine splitting. And here you can see if you introduce a finite u over t in a shallower lattice, you get these magnon. Okay. All right, so now you can vary u over t, and you can see the expected shift in the magnon spectra, and this would follow the t squared over u you would expect from the super exchange. I mean, of course, again, this is a doped system. If you had a system with no doping, those would all be eigenstates, and they would be narrow. They'd just be instrument resolution. But here we can see this clear broadening, which presumably is from the fact that we have holes in the system. And we're still trying to understand, maybe in a simple picture, what happens if you go to the limit of a single hole and you introduce these magnons. What's the story there? What's setting the increase in the line width? The temperature is of order 1. It's a little hard to get to low temperatures, because here you're starting with a spin polarized state. So it doesn't want to thermalize. So you kind of have to evaporate a spin imbalance mixture or something like that. And it's hard to get to low temperatures there. All right, and here you can see, in terms of the position of the peak, it obeys exactly this, the behavior you would expect from the t squared over u. And we're still trying to understand the width of the lines. And we're hoping now to apply this in the triangular case, and there you would expect these two peaks appearing, one for the magnon and one for the polaron. All right, so with that, yeah. Yeah, so far it's very crude. we don't have a setup which is varying this continuously. We literally go and tweak the mirrors and change the k vector. But so far, the few points we've tried is what you would expect from the magnon dispersion. OK, so with that, thank you very much for your attention.
Thank you, Waseem, for this great talk. So questions? Martin?
Yeah, it was a beautiful talk. One difference between this injection and ejection spectroscopy for me was always, if you eject, that means you already prepare the state and hopefully cold in the ground state, and then you just measure its basically wave function by going to the non-interacting final state. Whereas if you inject, you're not only talking to the ground state, but also to all excitations of that impurity that you inject. So I was always worried that the injection is always giving a bit a broader response than if you eject. Could you brainstorm on that?
I don't know. We've just been thinking about this in various limits. For example, one limit to think about is, let's go to half filling and large u over t. and then start to lower U over T. So I think there you expect two peaks, and one would be a very sharp peak, and then the other one would be you can create this thing that decays into a doublon and a hole, and there you would have a continuum, and that would lead to some broadening. Maybe that's an example of the kind of thing you're talking about. Yeah.
That would be nice to compare.
That's right. Yeah, yeah.
Okay, Timon?
So I have a question about the correlation that you saw with the polaron and the triangular lattice. So this antiferromagnetism and ferromagnetism that you favor there, is there something beyond the correlation? Does it at some point really lead to a phase transition from a theoretical point of view? Or how big are basically these changes? You said that the temperatures are relatively high that you have, but it's still on lower temperature. Is this known, or is this all too complicated for people?
I don't really know. I think that Eugene was showing some phase diagrams, but
yes.
Yeah.
So there is a phase transition basically of the doped system now as a function of doping, for example, where the effect overpowers the original.
Well, not as a function of temperature, but as a function of U over T and doping at different phases. So like when U over T is smaller, you get not more this polaronic phase, but some geometric.
Actually, maybe can you show again the nice slide where you had the evolution as a function of U over T?
Yeah.
Yes. So things are fairly, in a sense, fairly smooth, although.
Yeah.
I mean,
this is what I was saying. It's
yeah, I know.
It's a little bit disappointing that it's so smooth.
Well, but maybe it's
the
not that.
The difference might be this linear slope that kind of disappears here.
Imagine you're just being given this, right?
Yeah.
And no other information about the system, nothing about compressibility and so on.
Yeah.
Would you be able to get to guess where the say the filling, the metal insulator transition is just from C3? Perhaps, right? I mean, there seems to be clearly some.
I think.
Behavior,
Yeah.
the linear behavior we're mentioning, right, around zero doping.
Yeah. I mean, I think this is again where several probes would be helpful. So maybe the spectroscopy kind of adds more data.
The temperature is fairly, still of the order of.
Yeah. It's like 70%. Yeah.
So things are not that sharp.
Yeah.
That's quite interesting.
So you basically pretty mean like our theory knowledge, like at our feeling, we know that transition is around 9.
No, I know that too.
No, but that's why you are saying it's somewhere around 9, just because you actually know where it is.
Yeah. So that's why my question was: imagine I know nothing. I'm just given a C3. Could I guess?
No, because I guess it's because you are not thinking about transition. That what looks like is a function of doping, but at half filling as a function of U.
Correct.
Because it wasn't clear the way you formulated.
Oh, sorry. Yeah.
I mean, of course, we have C3, C2, and C1 in a sense. We have all the correlation functions.
Yeah. But still, the shape. Anyway,
Yeah.
It's kind of interesting.
Yeah, I mean, the fact that they have the same sign even in the non-interacting
Yeah,
limit.
but they don't quite have the same shape as
Yeah.
a function of around half
Yep.
as a function of doping. Okay. Any other question? Yeah, that's fine.
In the Raman part of the talk,
Yeah.
you mentioned that you had a resolution of about 1/8 the tunneling energy. Could you
Sorry?
comment on what sets that number?
Yeah. I mean, okay, I can tell you all the things we first had to fix, but now it's Fourier broadening. But and we had a lot of technical things we had to fix. I mean, things like you don't want to send your Raman beams through separate fibers because then you're going to get some fiber noise. There's a long set of technical things that are important to get to a good resolution. But I mean, there's here the Fourier broadening is you can always increase the time, but you want to lower the intensity because here with lithium the Raman there's a lot of scattering. So here what we're trying to keep the scattering sort of on the few percent level, 1 or 2% level. That's what's setting. So it becomes an issue of just patience of the students. You know, if you want to take that, you can increase your pulse time, reduce the intensity. You stay in the linear response regime, but just you need to average more to get good signal to noise.
What is the momentum transfer for those results?
Okay, so this one is it's a little funny. So what we set up the system for the triangular lattice, even though we were doing square, because we wanted to do it in the triangular lattice. And so the momentum is exactly the momentum which you would need for, I showed you have the band structure of the triangular lattice, and the holes sit at this finite quasi-momentum. So you want to flip the magnon at that quasi-momentum so that you get like a zero momentum polaron. So it's that momentum, but they just decided to try it first for the square lattice, for which this quasi-momentum is not relevant in any particular sense. Yeah.
But the quasi-momentum is a fraction of h per k or so?
Yeah,
it's
yeah,
two angled beams?
yeah. It's a good fraction.
As a follow-up, actually, you mentioned scattering.
Can you speak louder?
Yeah, sorry. As a follow-up, you mentioned that you see effects from scattering sometimes. How do you tell when you see that as opposed to the coherent part of the drive?
It's like the offsets that you're seeing in here. So you have to.
Because you have two states.
You have an excited state, and they're very close. Like basically, if you detune very far away, then you can't make a spin flip.
Yeah, that's right.
Or at least if you detune far away, the scattering goes as 1 over detuning squared, and the coherent coupling goes at 1 over detuning squared, so you don't win anymore. So I mean, the nice thing here is, so we can get a few Rabi oscillations, for example, for isolated wells, but you just need to sit at the beginning of the Rabi oscillation because it's all linear response. So you can make it look almost indistinguishable from not having any scattering.
Okay, more questions. Shiwei.
So I didn't quite catch. Is it straightforward for you to do a T prime squared lattice Hubbard model? In other words, having T prime in both directions.
So the thing we have here is just a T
You
prime
have
along one
right.
direction.
Is it easy for you to do the other one? I guess the first talk you also mentioned
You
this.
guys had some idea, I think.
We can do it because we have slightly different lattice geometry
Yeah, it's
beams, and
yeah.
was never sure if that one we can.
Yeah,
And
I
the-
don't think in our setup is straightforward.
And the magnitude can be dialed, or is it?
Because on band structure calculation, we can tune that from like 0 to like 30%.
So that's definitely something we should discuss more tomorrow during the panel discussion, because as you probably all know, T prime is a really important parameter for stabilizing pairing in the square lattice. Okay, more questions, remarks? Yes. Yeah, go ahead, Timo.
Maybe to the very first part where you just look at the spin correlations in the triangular lattice. Did you look at higher orders of like 4-point spin correlators or something like this? Is there something to find that basically shows you more insight into the non-trivial arrangement of those spins?
Different from what I showed you. I mean, I showed a 4-point.
Yeah, but no, I mean four spins. Just an undoped system. You just take the mod insulator on the triangular lattice, and you now basically correlate the spin correlations on one pair with another one that might give you some hints
Would you
into
expect
this.
it to be very different from just like the first order? It's that last picture there.
Yeah, but you want the spin resolution on the other ones. Here you're just conditioning it on this. So
Yeah,
I was
we
wondering
haven't
if one
tried
can
that,
basically
yeah.
find something about that 120-degree order out of those.
No, we haven't tried that. But I mean, it's possible.
Does someone know if that helps? If there is some information in this? Because you could do it, right? Because you have the full resolution, so in principle.
Is there something interesting to look for?
Oh, that was not a complaint. That was an interesting observation. I was not complaining about anything.
Yeah, we can certainly do it.
More questions? So we are almost precisely right on time. You know, this must be you AMO guys being so precise. so, so let's thank Waseem again.